Welcome back to Let's Get Rusty. My name is Bogdan, and this channel is all about the Rust programming language. If that sounds interesting to you, hover over that subscribe button and give it a fist bump. Last time we went over chapter 3 of the Rust Lang book, in which we covered basic programming concepts in the context of Rust. If you haven't already, check that video out. In this video, we're going to be talking about chapter 4, and this is a very special video because chapter 4 covers Rust's most unique feature, ownership. Ownership is what allows Rust to make memory safety guarantees without the use of a garbage collector. We'll also cover references, borrowing, the slice type, and how Rust lays out data in memory. So with that, let's get started. First, we'll answer the basic question, what is ownership, or the ownership model in Rust? The ownership model is a way to manage memory. Now you might ask, why do we need a way to manage memory? And to understand, it's helpful to look at the two other solutions for managing memory today. First, we have garbage collection. If you've ever written an app using a higher level programming language such as Java or C#, you didn't have to worry about memory management because the garbage collector did it for you. Now this approach has some pros and cons. The first pro is that it's error-free, meaning that if you were to manage memory yourself, you might introduce memory bugs. But since that's being handled by the garbage collector, you can be pretty sure that there aren't any memory issues. I put an asterisk because garbage collectors could have bugs themselves, but for the most part, you can be rest assured that your memory is being managed safely. The second pro is faster write time. Because you don't have to deal with memory, you can write your programs faster. Now let's look at the cons. Firstly, we're giving up fine-grained control of our memory. That's because the garbage collector now handles all our memory. Secondly, our runtime performance can be slower and more unpredictable. Slower because we can't manually optimize our memory, and unpredictable because the garbage collector could choose to clean up memory at any point in time, and when it does so, it slows down our program. Lastly, we have a larger program size because the garbage collector is a piece of code that we have to include within our program. Now let's look at manual memory management. If you've written C or C++, you have to allocate and deallocate memory manually. Now the pros of this is full control over your memory, which leads to a faster runtime because you can optimize things, and a smaller program size because you don't have to include a garbage collector. The cons are, first, it's extremely error prone. Many bugs and security issues are caused by incorrect memory management. And secondly, you have a slower write time. Because you have to think about memory, it takes longer to write your program. Notice here that the pros and cons of garbage collection and the pros and cons of manual memory management are the exact opposite. We're making opposite trade-offs here. Either of these solutions could be appropriate depending on the context. If you're writing a high-level app like a website, it makes sense to sacrifice runtime performance and have a larger program size for the ease of use and faster write time you get with a garbage collector. On the other hand, if you're writing low-level system components, then you probably care a lot more about runtime performance and program size, so it would make more sense to use manual memory management. Now we could talk about the ownership model, which is a third way to manage memory. Now, Rust is a systems programming language, so it does care about runtime performance and program size. And as you can see here, we get all the benefits of manual memory management, control over our memory, faster runtime, and smaller program size. Rust, however, is also a memory-safe language, so we can't use manual memory management because, as we said before, it's error-prone. And as you can see here, the ownership model is error-free. And the way Rust achieves this is by doing a bunch of compile time checks to make sure you're using memory in a safe way. Now, I put an asterisk here because even though Rust is memory safe by default, it does allow you to opt out of memory safety with the unsafe keyword, but that's meant to be used sparingly. As you might know, everything in software is a trade-off. So the ownership model gives us memory safety, but the con is we get a slower write time, slower than manual memory management. And that's because Rust has a strict set of rules around memory management. And if you break those rules, you'll get compile time errors you have to deal with. This is sometimes known as fighting with a borrow checker, and it could be frustrating, but as anything, with time you'll get better and things will become easier. The big idea here is that this trade-off is worth it. It's worth spending the time upfront dealing with the borrow checker so you don't have to spend hours and hours later debugging runtime memory issues. Now, because Rust is a systems programming language, it's important for us to know how our memory is laid out during runtime. Rust makes certain decisions based on if our memory is stored on the stack or on the heap. So next we'll briefly go over what the stack and heap are. During runtime, our program has access to both the stack and the heap. The stack is fixed size and cannot grow or shrink during runtime. The stack also stores stack frames, which are created for every function that executes, and the stack frame stores the local variables of the function being executed. The size of a stack frame is calculated at compile time, so that means the variables inside a stack frame must have a known fixed size. Variables inside of a stack frame also only live as long as the stack frame lives. So for example, in this program, A gets executed first, so we push A onto the stack. Then A executes B, so we push a stack frame for B onto the stack. Now when B finishes executing, it gets popped off the stack and all of its variables are dropped. Then when A gets done executing, all its local variables are dropped. The heap, on the other hand, is less organized. It could grow or shrink at runtime, and the data stored in the heap could be dynamic in size, it could be large amounts of data, and we control the lifetime of the data. Let's go back to our example. First, we execute the function A, which creates a new stack frame. A initializes the variables x and y. X is a string literal, which is actually stored in our binary. So in the stack frame, x here will be a reference to that string in our binary. Y is a signed 32-bit integer, which is a fixed size, so we can store y directly in the stack frame. Then we execute the function B, so another stack frame is created, and B creates its own variable named x. X is of type string, which could be dynamic in size, so we can't store it directly on the stack. Instead, we ask the heap to allocate memory for the string, which it does, and then the heap passes back a pointer. The pointer is what we actually store on the stack. Note that pushing to the stack is faster than allocating on the heap because the heap has to spend time looking for a place to store the new data. Also note that accessing data on the stack is faster than accessing data on the heap because with the heap, you have to follow the pointer. I know that was a very brief explanation, so if you're still confused or want a more thorough explanation, I put a link in the description of a video that goes into a lot more detail on the stack and heap, so make sure to check that out. Alright, let's get back to ownership. And before we go any further, there are 3 ownership rules that are crucial to remember. Write these down, put them in a Word doc, get them tattooed, whatever it takes. The rules are: 1. Each value in Rust has a variable that's called its owner. So 1 variable, 1 owner. 2. There can only be 1 owner at a time. So a variable cannot have 2 owners at the same time. And 3. When the owner goes out of scope, the value is dropped. As an example, I created a new scope here using the curly brackets, and inside I defined the variable s. Here, s is not valid because it's not declared yet. Then we declare s, and it's valid from this point forward. We could do things with s. Then when the scope ends, s is invalidated and Rust drops the value. S here is a string literal, and as I've mentioned before, string literals are stored directly in the binary and are fixed in size. So what if we wanted a string that's dynamic in size and that we could mutate? Well, we would have to use the string type. I went ahead and converted s to a string type, and now our string is stored on the heap. In programming languages such as C++, to allocate memory on the heap, you would have to use the new keyword, and then you would have to deallocate that memory using the delete keyword when you're done with it. In Rust, this happens automatically. When we declare s here, Rust automatically allocates memory on the heap for our string. And then when the scope ends, s is invalidated and Rust drops our value, meaning that it deallocates the memory on the heap automatically. Next, let's talk about how variables and data interact. Here we have 2 variables, x and y. X is set to 5 and y is set to x. And as you can tell by the comment, this is going to do what you might expect, which is copy the value 5 into y. Let's look at a more interesting example. Here we have the variable s1 and we set that equal to a string type. On the right hand side, you can see what s1 looks like under the hood. We have a pointer that's pointing to the actual memory location on the heap. We have a length, which is the length of the string, and we have capacity, which is the actual amount of memory allocated on the heap for our string. On the next line, we declare s2 and set that equal to s1. So what would we expect to happen in this situation? Some might expect the value to be cloned, like we see on the right-hand side. S1 is pointing to a string on the heap, and S2 is another pointer pointing to a new string on the heap. But this is not what happens, as it would be very expensive to create a new string on the heap. Others might think that we do a shallow copy. So S1 has a pointer that points to hello on the heap, and S2 has a pointer that points to the same hello on the heap. This is not quite what happens because to ensure memory safety, Rust invalidates S1. So instead of being a shallow copy, this is called a move. Going back to our program, let's try to print S1 after it's been moved into S2. We'll call it cargo run. And as you could see, we got a compile time error, which says S1 was moved here, and then we tried to use S1 after it has. What if we did actually want to clone the string instead of moving S1? Well, Rust has a common method for that. So instead of setting S2 equal to S1, we'll set S2 equal to S1 and we'll call the clone method on it. And now we can run our program and it compiles successfully. So Rust defaults to moving a value, and if you want to perform the more expensive clone operation, there's a method for that. There's one other detail here. Up above, when we set y equal to x, this did a copy, not a move. Rust has a copy trait that simple types stored on the stack, such as integers, booleans, and characters, implement. This trait allows those types to be copied instead of moved. Next, let's talk about ownership and functions. Here we have a variable called s, that's a string, and a function called takes ownership. The takes ownership function takes in some string as a parameter and then prints it out. In main, we try to print the variable s after we call it takes ownership, but we get an error. And the error states that s cannot be borrowed after a move. And that's because when we pass in parameters into a function, it's the same as if we were to assign s to another variable. So here, passing in s moves s into the substring variable. Then substring gets printed out, and after this scope is done, substring gets dropped. Let's look at another example. We have the variable x here that is an integer and a function called makes copy. Makes copy takes in an integer and then prints it out. Here you can see we pass an x, but instead of being moved, remember integers are copied, so it gets copied into the sum integer variable, printed out, but we can still use x after the function call. This also works the opposite way. Here we have a variable s1 that's equal to the return value of gives ownership. Gives ownership is a function that returns a string. And here you can see we create a string that's called substring, and then we return that string. Returning the string moves the ownership of the string to the s1 variable, and then we can use it afterwards. Lastly, we could take ownership and give it back. For example, here we have a variable called s2, which is a string, and we pass that into a function called takes and gives back. Takes and gives back takes in an argument that's a string called a string, and then just returns a string. So here we're moving the value of s2 into the function, and then we're just returning a string, which moves the value back out of the function into s3. Moving ownership into a function and back out is tedious. What if we just wanted to use a variable without taking ownership? Well, that's where references come in, and that's what we'll talk about next. To understand references, let's see how they could fix the following situation. Here we have a function called calculate length. What we want to do is take in a string and return the length of that string. However, we don't want to take ownership of the string. The solution here is to return a tuple that contains the string and the length of the string. Up here, you can see we assign the string to s2 and the length to a variable called len. You could also see that this looks very strange and probably not something you would ever want to write. To fix this, let's first modify our calculate length function. First, we'll change the return type to be just the length of the string. Next, we'll return just the length. Up above, we'll get rid of s2 and print s1 down here. As expected, we get an error here because we're borrowing s1 after it's been moved into the function. To fix this error, instead of calculate length taking a string, we'll make it take a reference to a string, and we do that by adding an ampersand before the string. Next, in the main function, instead of passing in a string, we'll pass in a reference to a string by using the ampersand again. Great, now we have no errors, and that's because s is a reference to a string, and references don't take ownership of the underlying value. Here in the Rust book, you can see a diagram of what a reference looks like. S is the reference, and it points to s1, which actually points to our string in the heap. S is a local variable inside of calculate length, and when the function finishes executing, S is dropped, but that's okay because if we drop S here, we still have S1 pointing to our string. Passing in references as function parameters is called borrowing because we're borrowing the value, but we're not actually taking ownership of it. Also note that references are immutable by default. So if we try to modify s here, you could see that we get an error, which says we cannot borrow the value as mutable. Here I have another example. We have a string and a function called change, which takes a reference to that string and then attempts to modify it. Again, references are immutable by default, so we can't modify the value. But let's say we actually did want to modify the value without taking ownership of it. To do that, first we'll need to make s1 a mutable variable. Next, instead of passing in a reference, we're going to pass in a mutable reference. Finally, we'll have the change function take in a mutable reference. Now the change function is able to mutate our string without taking ownership of the underlying value. Mutable references have a big restriction though, which is you can only have one mutable reference to a particular piece of data in a particular scope. For example, we have a string here and a variable called r1, which is a mutable reference to the string. Now let's add another mutable reference and print out both references. Here we have r2, which is another mutable reference to string, and then a print statement that prints out both r1 and r2. And you can see we get an error here. The error states you cannot borrow s as mutable more than once at a time. The big benefit of this restriction is that Rust can prevent data races at compile time. A data race occurs if we have two pointers pointing to the same piece of data, and one of those pointers is used to write to the data, and there's no mechanism to synchronize data access between those pointers. In that situation, you could imagine that one pointer will try to read the data in the middle of the other pointer modifying the data, and in that case, we'll get corrupt data back. To fix this error, we can switch these references back to be immutable references. And now we don't have any errors. But what happens if we mix immutable references with mutable references? Let's go ahead and add another variable. We'll also go ahead and make s mutable. But as you can see, we still get an error. Here we're running into another restriction. You can't have a mutable reference if an immutable reference already exists. Immutable references don't expect the underlying value to change, and this is problematic if we do have a mutable reference. You can, however, have multiple immutable references. It's okay to have multiple immutable references because the underlying data is not going to change. Note that the scope of a reference starts when it's first introduced and ends when it's used for the last time. So for example, R1 is introduced here, so the scope starts here, and it's used for the last time in this print line statement, so the scope ends here. This means that we can add a third mutable reference underneath this print line statement. And we'll make s mutable. And this works just fine because at this point, R1 and R2 are out of scope, so we can declare a mutable reference. Next, let's talk about dangling references. What happens if we have a reference that points to invalid data? Well, here we can see we have a variable called reference to nothing, and it's set to the return value of dangle. Dangle is a function that returns a reference to a string. Inside of dangle, we can see we have a variable called s, which is set to a string, and then we return a reference to that string. However, s is defined within the scope of this function. So when this function finishes executing, Rust will drop our string or deallocate our string from the heap. Therefore, our reference will be pointing to invalid memory. But as you could see, Rust prevents this from happening because we get an error here. If we hover over, we see that the error states this function's return type contains a borrowed value, but there is no value for it to be borrowed from. We don't have a value for it to be borrowed from because the value gets dropped. We also get a recommendation to use something called a lifetime. Lifetimes is something we'll talk about in chapter 10, but for now we can ignore it. The point here is that, again, Rust prevents us from doing something that's memory unsafe. To wrap up references, let's review the rules of references. Number 1, at any given time, for a particular piece of data in a particular scope, you can either have one mutable reference or any number of immutable references. And number 2, those references must be valid. The data they point to must be valid. The last thing we're going to talk about are slices. Slices let you reference a contiguous sequence of elements within a collection instead of referencing the entire collection. And just like the references we covered in the last section, slices do not take ownership of the underlying data. To understand why slices are useful, let's start with a problem. Imagine we have a function we want to write called first word. It takes in a reference to a string because we don't want to take ownership of that string, and then it returns the first word in that string. Looking at the function signature, what would our return type be? We don't have a way to return part of the string, but maybe we can return an index to the end of the first word. That implementation will look something like this. Here we're returning an index to the end of the word, and inside our function, what we do is we take the string and convert it into an array of bytes. Then we use a for loop. Here we take the bytes, call the iterator function, and then call enumerate so we can get the index of each item and the item itself. Then for every item, we check if it equals an empty space, which signifies the end of a word. And if that's true, then we return that index. If we go through this entire loop and don't find an empty space, then that means that the entire string is one word, so we can return the length of the string. There are two problems with this implementation. The first is that the return value is not tied to the string, and here's what I mean. In main, we have a string under the variable s. We pass that string to first word, and we store the return value in a variable called word. In this case, our return value is 5 because our first word is hello. H is at index 0, then we have E at index 1, LL at index 2 and 3, O at index 4, and the space is at index 5. Now the problem is on line 4, we call the clear method on our string, which makes it an empty string. So now our variable word is still 5 even though the string is empty. And again, this is because our return value is not tied to the string itself. This means we have to manually keep our return value in sync with the string, which is extremely error prone. The second problem comes when we want to change the implementation. Imagine instead of the first word, we wanted to return the second word. In that case, we would have to return a tuple with two values, an index to the start of the word and an index to the end of the word. And now we have more values that we need to keep in sync with the string. To get around these issues, let's introduce the string slice. Here underneath our string, we'll declare two string slices. Here we've defined two string slices, hello and world. They look very similar to string references, except we have this bracket syntax here with a range inside. This is saying give us a reference to the string, but we only want part of the string. Specifically, we want the part of the string starting from index 0 and ending at index 4. The 5 is exclusive here. And that will give us the word hello. On the second line, we're doing something similar, but from index 6 to 11, which will give us world. The Rust book has a nice diagram to show us what's going on. Here we have S, which is our string, and you can see it has a pointer pointing to the string on the heap. And then world is our string slice. That's a reference pointing to the same string on the heap, but starting at index 6. We can simplify these string slices a bit further. If we're starting from the beginning of the string, we can omit the 0 here. And if our range continues to the end of the string, we can omit 11 here as well. Lastly, if we want a string slice to span the entirety of the string, we can omit the first and second value here. In this case, world is a string slice that will reference the entire string. Now that we know about string slices, let's modify our first word function to take advantage of them. The first thing we'll do is change the return type from the index to a string slice. Next, if the first word is found, instead of returning the index, we'll return a string slice. Here we're returning a string slice from the beginning of the word to the index where the space was found. Lastly, at the end here, instead of returning the length of the string, we'll return a string slice to the entire string. Now our word variable is a string slice, which is tied to the string itself. And to prove that, let's try printing out word after we clear the string. And here we could see we get an error. Cannot borrow s as mutable because it is already borrowed as immutable. Word is a string slice, which is an immutable reference to string. And here we call clear, which mutates the string. That means we need a mutable reference. And if you recall, we cannot mix mutable and immutable references in the same scope. Let's get rid of the code that's erroring. And we'll create a new variable called s2. And we'll set it to a string literal hello world. As you can see, string literals are actually string slices. As I mentioned before, string literals are stored directly in the binary, but s2 here is actually a string slice to that location in the binary. Now let's say we wanted our first word function to also work with string literals. In that case, it would have to take in a string slice. So let's change that. Notice that our call to first word here kept working. This is because our string reference gets automatically coerced to a string slice. And now we can pass in s2 and our function still continues to work. And notice here that strings have the type of string with a capital S, and string slices have their type written as ampersand lowercase str. We can also have slices on different types of collections. For example, we have an array here. Let's say we want to create a slice on this array. So we'll create a new variable called slice. And we'll set that equal to a portion of the A array. Here you could see we use a similar syntax. We have the ampersand A for the A array and then brackets, and here we do a range from 0 to 2. So our slice here references the first two values in the A array. And you can see here, instead of the type being ampersand str, it's ampersand curly brackets I32, because the array stores a list of signed 32-bit integers. And there you have it, chapter 4 of the Rustling book complete. We learned about ownership, memory management, references, borrowing, the slice type, and much more. If you like this video, make sure to give it a thumbs up, and if you want to see more Rust content, make sure to hit subscribe and the notification bell so you can be notified when the next video comes out. I'll see you in the next one.
Today I'm going to help you master your understanding of the option Greeks using helpful visualizations, examples, and logical explanations when possible. The option Greeks are essential to learn as an options trading beginner because they inform you of the risks that your option positions are exposed to. The first option Greek you need to understand is called delta, and delta predicts an option's price change relative to a $1 shift in the stock price. In essence, it's the sensitivity of your option's price relative to changes in the stock price. We can visualize delta by using an options pricing calculator, plotting the call prices at various stock prices. So consider a call option with a strike price of $200 and 90 days until expiration. As you'll see, the call price increases when the stock price rises, and the call price falls when the stock price declines. This is because call options have positive deltas, and that means that the call option's price will move in the same direction as the stock price. Let's say you have a call option with a delta of positive 0.5. This implies that if the stock price goes up by $1, your call option will experience a 50-cent price gain. Conversely, if the stock price goes down by $1, this call option should lose about 50 cents. Let's look at a real-life example using Apple data. In this Apple call chart, note the relationship between the stock price, the price of the 135 call, and the call's delta. Initially, the call's delta was approximately 0.47, suggesting the call's price would change by about 47 cents for the initial $1 changes in the stock price. When Apple shares rose from 132 to 136, an increase of $4, the call's price climbed from around $7 to $9, or a $2 increase. And this is consistent with that positive 0.47 delta that the call had at the beginning of this period. Now, put options have negative deltas, and this means that their prices move in the opposite direction as the stock price. So if the stock price goes up, a put options price will fall, and if the stock price goes down, a put options price will increase. And again, we can visualize this using an options pricing calculator to plot the put option price at various stock prices. So here we see the put options price is increasing as the stock price goes down, and the put options price is decreasing as the stock price goes up. And this visualizes negative delta. Call option deltas can range from 0 to positive 1, and put option deltas can range from 0 to negative 1. So an option's price can only be as sensitive as a share of stock itself. But option deltas do not remain constant, they do change, and this brings us to our second option Greek to understand, which is called gamma. Gamma is the option Greek that estimates how an option's delta will change given a $1 shift in the stock price. So as delta is predicting how the option's price will change given a $1 shift in the stock price, gamma is predicting how the option's delta will change when that stock price movement occurs. Let's go back to our earlier Apple example to visualize this. In this example, you'll see the call's delta rising alongside the stock price. Gamma predicts this rate of change, estimating the adjustment in an option's delta for a $1 movement in the stock price. Consider a call with a delta of 0.5 and a gamma of 0.05. Here, if the stock price increases by $1, the call's delta would become a positive 0.55. Conversely, if the stock price drops by $1, the delta would decrease to a positive 0.45. So what this means is if you own a call option and the stock price increases, your new call option delta is going to be higher than it was before, and therefore your option's price will be more sensitive to changes in the stock price compared to when the stock price was lower. And conversely, if you own a call option and the stock price falls, your call option is going to become less sensitive to changes in the stock price than it was before. The opposite is true for put options because a put option's delta will get closer to -1 as the stock price falls, meaning its price will become more sensitive to changes in the stock price. And if the stock price increases, put option deltas will move towards 0, which means they will become less sensitive to changes in the stock price than they were before. In the Apple example, the call began with a delta of positive 0.5, indicating a 50-cent change for each $1 shift in the stock price at the beginning of the period. However, by the end of the period, the call's delta was positive 1, suggesting a $1 change in the call price for each $1 shift in the stock price. And this implies that the call option is behaving more like shares of stock, because if the stock price rises by $1 and the option price rises by $1, this means that the option is trading just like shares of stock. And this is expected because in the Apple example, The stock price far exceeded the call's strike price at the end of the period, and this indicated a high likelihood that the call option would expire in the money, and when a call option expires in the money, it becomes 100 shares of stock. And so what that means is this call option was starting to trade like what it would become, and that's because with the stock price way above the strike price, this call option had a high likelihood of becoming or expiring in the money and converting into shares of stock. And so before the call option even became shares of stock, it started to trade like what it would become. I hope that makes sense. In this sense, we can understand delta as the probability of an option becoming shares or expiring in the money. If an option has a low delta or close to zero, it has a small probability of becoming shares and will behave less like them or be less sensitive to changes in the stock price. Conversely, if an option has a high delta, meaning it is close to positive or negative 1, it has a high probability of becoming shares at expiration, and therefore it will trade much more like shares of stock, experiencing a $1 change in the option price for a $1 change in the stock price. So if we interpret delta as the estimated probability of an option expiring in the money, which it sometimes is used as that proxy, then we can understand gamma as the change in the option's probability of expiring in the money as the stock price changes. So for example, if we have a call with a delta of 0.5 and a gamma of 0.05, this tells us that if the stock price goes up by $1, the delta is going to increase to 0.55, indicating a higher chance of expiring in the money at expiration. This makes sense because if the stock price is increasing towards that call option strike price or even above it, that means that the probability of the stock price being above that call's strike price at expiration is increasing. And so therefore the delta increases, making the option more sensitive to changes in the stock price since it has a higher probability of becoming shares of stock at expiration. The third option Greek to understand is called theta. Theta predicts the expected decrease in an option's price over time, assuming no change in the stock price or expected volatility. So consider this option price simulation with a 90-day call option and a $200 strike price and a volatility of 20%. If we keep the stock price and expected volatility constant, the call's price diminishes from $8 to $0 over the 90-day period. Theta gauges the estimated daily depreciation of an option's price if the stock price and expected volatility remain unchanged. Option prices are essentially a function of how likely they are to be valuable at the time of expiration. Generally speaking, option prices will fall as they get closer to expiration because with less and less time before those options expire, we have a smaller probability of seeing big stock price movements, and with a smaller probability of big stock price movements comes a smaller probability of big option price movements, and therefore the options price will get smaller and smaller as expiration approaches. The fourth option Greek to understand is called vega, and vega indicates the expected changes in an option's price corresponding to a 1% shift in implied volatility. Implied volatility reflects the anticipated fluctuations in a stock's price over a specific period as implied from option prices. For instance, consider two $100 stocks, and we're looking at 30-day call options with the same strike price on each of these stocks. Let's say the first stock has a call priced at $5 and the other stock has the same call priced at $10. The second scenario results in higher implied volatility because the elevated option price suggests that the market is anticipating more stock volatility over the next month in that second scenario as opposed to the first stock scenario. Vega is the option Greek that informs us how an option's price is expected to change given a change in implied volatility. So look at this 60-day Tesla call option with a vega of 0.31. This suggests that if the implied volatility increases by 1%, the option's price is expected to rise by 31 cents. If the implied volatility decreases by 1%, the option's price is anticipated to fall by 31 cents. Earlier, I mentioned that option prices are essentially a function of how likely they are to be valuable at the time of expiration. And so an increase in expected stock volatility will inflate all option prices because with larger anticipated stock price movements comes larger potential option price movements as well. And on the other hand, if the expected stock volatility decreases, that means there is smaller potential option price changes and therefore a decrease in expected stock volatility will deflate all option prices. So using an option pricing simulator, let's look at a 200 strike call option on a $200 stock, and let's plot the prices of these two different call options, assuming different levels of expected volatility. Assuming the stock price remains constant and no time passes, if you bought the call when implied volatility was 20% and it immediately rose to 30%, you'd profit from the increase in option prices. However, if you bought the call when IV was 30% and it dropped to 20%, you would lose money due to the deflation in option prices as the market factors in lower expected stock price volatility. Of course, volatility changes will coincide with some passage of time and sometimes significant stock price changes. But this simulation shows us just how the option price is expected to change given changes in volatility expectations. So far, we've talked about the individual option Greeks, meaning the expected price changes of an option as related to various factors. But now I want to look at position level Greeks, which tells us how much we can expect an entire option position to make or lose given a change in the stock price, the passage of time, or a change in volatility. So for instance, this position here has a delta of plus 175, gamma of plus 7, theta of negative 2.8, and vega of plus 81. This translates to a potential gain of $175 if the stock price goes up by $1 and a $175 loss if the stock price falls by $1. The gamma of plus 7 indicates that if the stock price goes up by $1, the position delta will increase by 7 points, and if the stock price goes down by $1, the position delta will decrease by 7 points. The theta of negative 2.8 tells us that if the stock price and volatility remain the same, then this overall position should lose $2.80 with the passage of 1 day. Finally, the vega of plus 81 suggests that if implied volatility goes up by 1%, this position should make $81. And if implied volatility falls by 1%, this position should lose $81. Now this might be a little confusing to you because earlier I mentioned that call deltas can only range from 0 to positive 1, and put deltas can only range from 0 to negative 1. So how do we get a delta of plus 175? The answer is that we have to account for the option contract multiplier. What I mean by that is if we have an option that is worth $2.50, we actually have to buy that option with $250 because we have to multiply that listed price by 100 since each option corresponds to 100 shares of stock. And a 50-cent change in an option price is actually a $50 profit or loss when you have a position in that option. So if you buy a call option for $2.50 and its price increases to $3, that represents an actual $50 profit on that option position. So the position delta in that case would be positive 50. Another example, if an options trader buys 5 call options and that call option has a delta of 0.5, that means they will make or lose $50 for a $1 change in the stock price, and therefore their delta or position delta would be a positive 250. Because if the stock price goes up by $1, they will have a $50 gain per option times 5 contracts, which gives them a $250 gain if the stock price goes up by $1 and a $250 loss if the stock price goes down by $1. The next thing I want to do is to go a little bit deeper on theta and vega because the Greeks theta and vega only affect the option's extrinsic value, not its intrinsic value. So time decay, or the loss of an option's value over time, only impacts extrinsic value, not intrinsic value. The intrinsic value of an option, or the amount that it is in the money, remains unaffected by the passage of time. This means if we have a call strike of 135 and the stock price is at 150, this call option will have intrinsic value of $15 since it has the ability to purchase shares of stock for $15 less than the current market price of the shares, and the value of that will never change no matter how much time passes or no matter how much volatility changes. Changes in implied volatility also only relate to extrinsic value, not intrinsic value. I really hope you enjoyed this Option Greeks for Beginners tutorial. My name is Chris from Project Finance, and I will see you in the next video.
In 1997, Myron Scholes and Robert Merton received the Nobel Memorial Prize in Economics for work that helped answer one of Wall Street's hardest questions. What is an option worth? At first glance, that sounds simple. A call option gives you the right to buy a stock later at a fixed price. But once the stock price is uncertain, time is passing, interest rates matter, and volatility changes everything, that right becomes surprisingly hard to value. This is the Black-Scholes model, one of the core frameworks that turns uncertainty into a theoretical options price. By the end of this video, the goal is not just to recognize the formula, it is to understand what the equation is doing, why bell curves show up, and why the assumptions matter. Before 1973, options pricing was far less standardized. If you wanted to buy the right to purchase a stock at a certain price, how much should you pay for that right today? Traders had no widely accepted, consistent way to answer that question. Then Fisher Black, Myron Scholes, and Robert Merton came along with a breakthrough. They showed that under specific assumptions, an option could be replicated by continuously adjusting a hedge made of the stock and cash. And that is the economic insight. If two positions can produce the same future payoff, they should have the same price today. Otherwise, traders could create an arbitrage. The result was a formula that gives a theoretical no arbitrage price for an option based on 5 main inputs. For this video, we will focus on the basic Black-Scholes formula for a European call option on a non-dividend paying stock. At expiration, the payoff is straightforward. If the stock finishes below the strike price, the call expires worthless. If the stock finishes above the strike price, the call is worth the stock value minus the strike price. So the payoff is easy to describe at expiration. The hard part is figuring out what that uncertain future payoff is worth today. That means the model has to answer 3 questions at once. How likely the option is to finish in the money, how much the stock can move, and how future cash flows should be discounted back to today. Here is the Black-Scholes call option formula. C is the theoretical call option price, S is the current stock price, K is the strike price, T is the time to expiration measured in years, R is the risk-free interest rate, sigma is volatility, and capital N is the cumulative normal distribution, which we will unpack visually in a minute. The most important intuition is that the formula has 2 big pieces. A call option is valuable because it gives you stock upside if the option finishes in the money. But to get that stock, you have to pay the strike price. So the model is roughly value of the stock side benefit minus the present value of the strike side cost. So this is not just 2 pieces glued together. It is the call payoff logic translated into today's dollars under the model's assumptions. D1 and D2 are not new market inputs. They are intermediate values the model calculates from the 5 inputs. Here is D1. You do not need to derive it to understand the model, but the pieces are useful. The ln of S over K is the moneyness term. It compares the stock price to the strike price. The R plus sigma squared over 2 term comes from the model's log normal pricing setup. And the denominator, sigma times the square root of T, scales everything by the total volatility over the life of the option. D2 is simpler. D2 is just D1 minus sigma times the square root of T. In other words, D2 is D1 shifted down by the total volatility over the option's life. The key idea is that D1 and D2 turn the option setup into locations on a standardized bell curve. Once the model has those locations, it can convert them into areas under the curve. Why is there a bell curve in an options formula? Because Black-Scholes assumes the stock follows a process where log returns are normally distributed. The stock price itself is modeled as log normal, but the log returns are what produce the bell curve. The model then standardizes the problem, so D1 and D2 can be read as positions on a standard normal curve, a bell curve measured in standard deviations. Capital N means the cumulative standard normal distribution. Put simply, n of x is the area under the bell curve to the left of x. It is an area, not the height of the curve. If you pick any point on the curve, call it D, then n of D is the area to the left of that point. Because it is an area, it is a number between 0 and 1. If D is positive, the area to the left is more than 50%. For example, n of positive 0.5 is about 0.69. If D is negative, the area to the left is less than 50%. N of negative 0.5 is about 0.31. Because the standard normal curve is symmetric, the negative version is the complement of the positive version. So n of negative D equals 1 minus n of D. That is why positive and negative versions of D1 and D2 are closely related. For calls, the standard formula uses n of D1 and n of D2. For puts, the standard formula uses n of negative D1 and n of negative D2. Same bell curve, different side of the option payoff. Now we can connect this directly to the option. In the Black-Scholes call formula, n of D2 is the model implied probability that the option finishes in the money. More precisely, it is a risk-neutral probability. That does not mean investors are actually risk-neutral. It means the model uses a pricing framework made possible by the hedging argument. If the option can be replicated by a continuously adjusted hedge, the model does not need your personal expected return for the stock. It prices the option using the risk-free rate and risk-neutral probabilities. This can feel a little backwards at first because a call finishes in the money when the stock is above the strike. But after the model standardizes and rearranges the problem, that event maps to the area to the left of D2 on the standard normal bell curve. N of D1 is different. In the basic Black-Scholes call formula, N of D1 is the call option's delta. Delta tells you how much the option price tends to move for a small move in the stock price. It is also the hedge ratio, the amount of stock exposure used to hedge the option in the model. So N of D1 and N of D2 are related, but they are not the same thing. N of D1 is tied to delta. N of D2 is tied to the risk-neutral probability of exercise. Now the formula should feel less arbitrary. The first term, S times N of D1, is the stock side value. The second term, K times E to the negative R times T times N of D2, is the strike side cost. E to the negative R times T is the continuous compounding discount factor. It brings the strike price back to today's dollars using the risk-free rate. Let's use a simple example. Suppose the stock price is 100, the strike price is 105, timed expiration is 6 months, the risk-free rate is 5%, and volatility is 20%. When you plug those into D1 and D2 formulas, you get D1 of about negative 0.1 and D2 of negative 0.24. The bell curve then converts those into N of D1 of 0.461 and N of D2 of about 0.406. Now substitute those values into the formula. The stock side value is about 100 times 0.461 or 46.1. The discounted strike is 105 times E to the negative 0.025 or about 102.41. Multiply that by 0.406, subtract it from the stock side value, and the model price comes out to about $4.58. That is not a promise that the option should trade at exactly that price in the real world. It is the theoretical price the model gives you when those inputs and assumptions are used. This also explains why you sometimes see N of negative D1 and N of negative D2. Those appear in the standard put option formula. A call payoff focuses on the upside above the strike. A put payoff focuses on the downside below the strike. So the put formula uses the complementary areas of the same bell curve. For example, if N of D2 is about 0.406, then N of negative D2 is about 0.594. Same curve, same model, different side of the payoff. Now that the formula makes more sense, the assumptions matter even more. Black-Scholes is powerful because the assumptions make the math work, but those assumptions are simplified. The basic version assumes the option is European style, meaning it can only be exercised at expiration. It assumes no dividends. It assumes volatility stays constant. It assumes you can trade continuously. It assumes no transaction costs. And it assumes stock prices move smoothly according to a log normal process. Real markets are messier. Prices can jump. Volatility changes over time. Trading costs money. And different strike prices often trade with different implied volatilities. That is why traders often treat Black-Scholes as a baseline rather than a perfect description of reality. It gives a disciplined starting point, but real options markets reflect volatility smiles, skews, jumps, and fat tails that the basic model does not fully capture. So Black-Scholes is not just a formula to memorize, it is a way of translating a call option's payoff into today's dollars using payoff logic, bell curve probabilities, discounting, and no arbitrage reasoning. Used carefully, it is an incredibly useful framework, but the price it gives is only as good as the assumptions behind it. Subscribe for more finance videos just like this one.